Hello, Shubhangi ma'am, and all the participants. Am I audible? Hello. Yes, ma'am.
Yeah, you are audible.
Okay, thank you, ma'am. Thank you for confirming. So, before starting our session, I'd like to brief all our participants about our speaker today. So, first of all, I'd like to greet everybody. So, good afternoon, everyone present here, respected Shubhangi ma'am, and all the dear participants. It is my pleasure to introduce our today's speaker, Dr. Shubhangi Chaturvedi, currently serving as Assistant Professor at IIIT University, Gwalior. Dr. Chaturvedi has recently completed her PhD in Computer Science and Engineering, where her research focused on deep learning models for real-time fire and smoke detection. She has published several research papers in top journals and have been actively involved in teaching, training in areas like deep learning, computer vision, and artificial intelligence. We are delighted to have her with us today for this insightful session. And she's also a recipient of the Young Scientist Award and has served as a speaker and resource person in various national FDPs and SDPs. We are so happy and delighted to have you here with us, ma'am, for taking your time from your busy schedule and giving us these insights on these topics. So I'd like to welcome you.
Thank you for
Yes,
the
ma'am.
introduction.
Yes. You
Uh,
can please share your screen and we can start with the session.
yeah. Uh, so I'll be sharing my screen and we'll be starting with the lab session directly on generative adversarial networks by building it on the PyTorch library. So let me share. Okay, so I hope that you must be knowing how to open the collaboratory file. So for collaboratory file, we have to right click on the drive where we'll be creating our new file today. And on that, we'll be creating, first of all, a generative adversarial network with small CNNs applied onto it. And then we'll train it. So I'm clicking on more and then going into the Google Collaboratory so that my file would get opened. So here, once the file is getting open, here then we'll be renaming it by whatever name we can give. So I am naming it as GAN lab for data augmentation. Then we would every time require some of the libraries that are needed for the model building. So first of all, we'll have our first step would be to import some of the useful libraries that would be required during the building of model. So first of all, we'll have to torch, import torch, then import torch.nn as NN. So we are aliasing it as NN for the neural network. So for taking the CNNs on any other layer, we would be requiring a neural network that would be imported using the torch for PyTorch model building. So we then the optimizer would be required. So for optimizer, we have to import the library torch.optim and we name it as optim. Then the another library is import torch vision, torch vision, torch vision. Then from torch vision, we have to import data sets. The data set that we'll be using today is CIFAR 10 dataset. and we also require transforms for providing some of the transformations that we would be requiring for giving the input to the neural network. Before giving the image to the neural network, some of the transformations or the normalization things are required. For applying these type of things, we require transforms from torch vision library. Then we have to import import matplotlib.pyplot as PLT. Then we are aliasing this matplotlib.pyplot as PLT. And then we require import numpy as NP. These things are required just for some of the things that we would require to uh, visualize the figures and all when we are about to augment the data. So one important step that we require is that we would require to set the device. So now we are about to set the device. This means that if we are having a CPU or a GPU, so if we are having a GPU, then we'll be assigning the GPU, the model would be assigned to the GPU so that the processing can be made faster. So we have to write device is equal to torch dot device, and then we'll be giving CUDA. And a condition would be checked at this time. If torch dot CUDA dot is available, is available, then the CUDA environment or the GPU would be given. Otherwise, if suppose we are not having the CUDA, then the CPU would be allotted. So for that condition, we have to give else CPU. So once this is done, we can run the cell. So initially, I am not having any of the GPU. First of all, I have not attached the GPU right now. So it would be running on the CPU for time. Uh, but then if we attach the GPU, then it is going to run the CUDA environment. So if it returns true, if this particular thing returns true, if then the CUDA GPU would be there on your system and it would be run. And if a GPU is available, then CUDA would be run. Otherwise, it is going to fall for the CPU part. So this was about this part, importing the basic libraries and setting up the device. Then after this, we move for some of the basic transformations that are always necessary for uh, normalizing the thing and to transform some of the things. So we will define some of the basic transform, define a basic transform. Here we'll be taking transform equals to transforms dot compose compose, and inside this we have to give the transformations that we are about to give. So I'll be giving transforms dot to tensor. We'll be converting the input to tensor form. For this, we have to give transforms dot to tensor. Then I also require the normalization for the images. So for this, I would be giving transforms dot normalize, and inside this we have to give the mean and standard deviation for the three channels of the images. So today's task we are about to do is we will be augmenting the data on CIFAR 10 data set. These are this data set contains images, so we'll be using it online and we'll be loading the data set. So before giving it the data set to the neural network, we require it to be transformed in some way. So we'll be normalizing it by using the mean and standard deviation. So these images are in RGB form. Three channels are there. So each channel would be having the mean and standard deviation. So we want to transform these three channels and we are giving the mean and standard deviation over here. So we are having 0.5 value for three channels, mean and standard deviation. 0.5 and then 0.5. So this code simply tells This code simply defines the transformation pipeline using the PyTorch vision.transforms. This particular cell that we have written, which is typically applied to images before they are fed into the neural network that I have told you. So the transforms.compose, the first line that we have written, this chains the multiple images that we are going to transform. So these all transformations come together by using the transforms.compose. So each of these transformations is applied in particular order. So first of all, we have done it in to convert it to tensor and then into the normalization. So in this case, we have used two of the transformations. First of all, we have used to tensor and then to normalize it. So the tensor, it usually converts the images to the PyTorch tensor form and transforms to normalize. It normalizes the image tensors using the given mean and standard deviation for each of the channels RGB. The three channel images that we have supplied, on that it is going to perform the transformation on mean and standard deviation. So it would scale the values on the range of -1 to 1 to perform these transformations. This is actually commonly done in GAN because it can center the data around the zero, and then it speeds up the code, and it also helps the model to converge well. So these are the basic requirements why we require the transformation over here. Then after that, what next thing we would require is the data set. That is the most important thing. So for that, we'll have to download the data and we have to make the data loader for it. So we have train data set. That is where my data set would be there. So in this train data set, we'll be downloading the data set. So data set that we have imported at the from the library Torch Vision. From Torch Vision import data set we have taken. So here we'll directly be using data sets dot CIFAR 10 data set, and inside this we'll be giving root is equals to dot and slash data. So from this particular root directory, directly the data set would be loaded. And after that, we have to train it. So we require the trained data. And then we want the data set online. So we would have to download it. So download the data equals to true. Download equals to true. and apply the transformations that we have done in the previous step. Transformed is equal to transform. Then next, I want to make a data loader where the batch of these images would be present. So for that, a data loader would be made. So for this, I require torch dot utils dot data loader that is going to load the data and then pass the trained data set on where we have downloaded the data trained set from the CIPAR 10 data set. Trained data set and set the batch size of 32. And we give shuffle as true. So during the training, shuffling would be given. So to set that thing, we are initializing shuffle as true. Okay, so till here, you can type if you are all are doing with me, then you can write till here. Once again, I explain that what we are doing. We are using the data set, CIPAR 10 data set, this particular line, the first particular line, it uses the training data set object using the CIPAR data set, and then it has a path dot slash data from this is the particular folder from which the data would be loaded. So if we make train equals to true, so there are two different set for this data set. Training and testing, we require only train data set on which we are going to perform the data augmentation. So to select that particular set, we have initialized this train set as true. And then we are about to download the data set. It's not already present inside this particular path, so we'll be downloading it. So so we have to set download equals to true and then perform the transformation which we have done in this particular step. So this thing is done here. After this, the second line where we have used torch.utils.data.beta loader, it wraps the train data set that we have used in the first line, that it wraps the train data set in the data loader to automate the batching and the shuffling process that we have initialized over here. So the data set we want to use, we have loaded it with the batch size of 32 and shuffle equals to true. So it shuffles the data at the beginning of each of the epoch and it helps the training by preventing the model from learning the order of the data. So it helps during the training process. So I'll wait for half a second so that if someone is writing, they can complete the task. So this data set actually consists of images in 10 different categories. CIPAR 10, its name is CIPAR 10. So it has 10 different categories, namely as aeroplane, it has automobiles, birds, images with birds, cat, deer, and various other animals are also there, like horse, frog, etc. And some of the automobiles are also present, like truck, etc. So there are basically 10 categories that this data set consists of the images. So overall, it has 60,000 around images that are broadly classified into 10 classes with 6,000 images per in each of the class. So the next, we'll move to the next step with this, with setting up of some of the hyperparameters that would be required during model training. So we would be hyper parameters. So we require the latent dimension. We would be setting it as 100. Then learning rate we will set as 0.0002. Then beta, that is used by the optimizer Adam that we are about to use. We'll be using Adam optimizer. It requires this hyperparameter for training the model in a better way. Then another is beta 2 that is initialized with 0.999. The number of epochs for which we'll be performing the training is 100. So we'll run this code and let me explain these hyperparameters that we have used. So we require latent dimension as 100. This actually set the size of the latent vector input. That input would be given to the generator part. So this latent dimension gives set the size of the latent vector, that the noise vector that is going to be given as an input to the generator. The generator takes random vector shape of 100 and it learns to map it to the realistic image. So its function would be to generate the new image. Generator is going to generate the new image using this latent dimension. The next hyperparameter is learning rate of 0.0002. This learning rate is used by the optimizer Adam that we would in future would be using, and it actually controls how much the weight updation would be done or how it is going to update the weights. So it this particular value is chosen because the GAN, the DC GAN original paper that was proposed, in that the learning rate was set as this particular value. So that is the reason that I have also used this. So using a very high learning rate is makes it unstable during the training, and using a very low learning rate, it slows down the learning capacity of the model. So beta 1 and beta 2 values are also chosen according to the generative adversarial original the first paper that was used by that was proposed by Ian Goodfellow. So he has also used this thing. So that is the reason that I've used these particular values. And the number of epochs, so it's going to the model would be going to iterate to 100 epochs. So 100 times it is going to iterate through the data set, and it's going to iterate through these number of epochs. So you can increase if you require to train your model for more number of epochs, so you can increase it as well. The next step that we are about to go is the generator step. We are going to build the generator next. So we are about to define the generator. So we will define the generator. Here, we'll be using some of the convolution layers, ReLU, batch normalization, etc. These types of layers would be used for building the generator models. So we begin with making it by using the class. Class name of this class is generator. This generator, inside this class generator, we are having neural network dot module, nn dot module. 'Module'. def init, and then the cells, comma, latent dimension, that the noise that is being supplied to the generator model. So this generator model would be having 2 or 3 layers of convolutional neural network, CNN, and then it would be also followed by the batch normalization and the ReLU activation functions. So we'll be using some of these layers in our model by building a sequential model. So now we are all set to build a sequential neural network. The code that we are about to write is the goal of this generator network is that it takes a random noise vector and it is going to produce the realistic images. So the class generator nn dot module, this we are defining as a custom PyTorch neural network module for our generator. The def init self latent dimension, it uses the noise, the size of the input noise vector as an input to this, and then it has a generator model is built as a sequence of layers using the sequential model, neural network dot sequential, that we are about to build. So let's begin with the sequential model. We have self dot model nn dot sequential, inside which we are going to write the layers. So first of all, we are using neural network dot linear and passing the latent dimension. Latent dim with the size of 128 by 8 by 8. After this, we'll be having a ReLU, nn dot ReLU activation, and then we have to unflatten it. So neural network dot unflatten 1 comma 128 comma 8 dot comma 8. So we are initially taking a linear, layer, or we can say a fully connected dense layer over here with the noise, vector that has the size of 100 to a tensor of size. We are changing it to a tensor of size 128 by 8 by 8. That would be giving some of the a total overall value. So the next activation that after this we are supplying is the neural network dot ReLU. This activation is going to introduce a non-linearity to the model. And then we have, once we have given a one-dimensional over here, the 128 into 8 into 8 is going to result to 8192 value. So this is going to be reshaped by using the neural network dot unflatten by into 1 by 128 comma 8 comma 8. So it is simply going to reshape the flat vector into a feature map with shape of 128 channels and 8 height and 8 width. So this is simply reshaping the thing that is given from the linear layer. So after this, performing these, after writing these three lines into the generator model, after this we have to upsample the features that we have got from the unflattened one. The DC GAN, the deep convolutional generative adversarial network, which was originally built, it uses a combination of convolutional CNNs, batch normalization, and the convolution 2D, con 2D transpose. So we are using here the upsampling layer for upsampling the features to certain dimension. So we will upsample by a scale factor of 2. Factor equals to 2. And then apply the convolution to these features. So now I will apply convolution layer, con 2D, con 2D, and inside this I have to give the two of the values, that is 128 and 128. The first 128 is the input channel, the another one is the output dimension. Then then we'll be giving the kernel size and the padding. So 128 is input, 128 is the output size, and kernel is set to 3. Kernel size is set to 3. Padding is 1. Padding is equal to 1. After adding the layer of convolutional neural network, CNN, the con 2D, after this, I'll be adding batch normalization. So NN dot batch norm 2D, 128 and set momentum as 0.78. NN dot ReLU. So we are applying non-linearity after this con 2D layer. To apply that, we have used ReLU activation function. Then once again, let's upsample the features that are given by the batch normalization or the convolution layer. So for upsampling, again, we'll be using a factor of 2. So upsample scale factor of 2. Then again, once again, let's apply con 2D. Con 2D. In this, the output coming from the previous convolution 2D was 128. So I would be giving 128 over here. Then the output size would be 64. Kernel size is 3. Padding is 1. Then apply again a batch norm. Batch norm 2D. Inside this, 64 is the output dimension that we would be using. Then again, we'll be using the ReLU activation for applying the non-linearity to this convolution layer. And once again, let's use a convolution 2D. One more layer for conv 2D, conv 2D. Here, this output dimension from the previous conv was 64. Now we would require a, this is the last conv that we are about to use. So this last convolution would be having the output dimension of 3 channels for the image that is being generated by the generator. So it is having output channel as 3, then kernel size is set as again 3 and padding as 1. This time we'll be using 10H activation at the last of this last convolution. After this, we will be adding non-linearity by using the 10H activation function. After this, we would have to give a forward pass for the training of this generator. So we'll define def forward during when the forward propagation, backward propagation would be taken. So for that, these things are required. So we'll be defining forward path, def forward self, comma z, and pass and give the image img is equal to self dot model of the z and return the image that it has generated. So here I have forgot to put the comma and first the error. And I have again run this code. So what we were doing is, let's see one quickly once the what we were about to do. From here, once we have unflattened the features that were coming from the previous linear layer. We have upsampled the image to by the factor of 2. So if that was 8 by 8, it is going to be 16 by 16. Then again, we have applied convolution 128. Input was given as 128 and 128. That is the in channels, and another 128 defines the out channel. The kernel size is defined as 3, and we have supplied the padding. And then a batch norm 2D is given, and then non-linear to add the non-linearity, an activation of value was given. So batch normalization helps in achieving the stability in the training. So it normalizes the activation and it helps in stabilizing the training. So it helps for during the training process. Then we again upsample the features by the factor of 2. So if suppose it was 16 by 16, it is going to be 32 by 32 by upsampling by this scale factor of 2. Then the convolution 2D, it what it does is it has in channel is 128, which was supplied from this convolution part above. Out channel was 128, so here in channel is 128, and its out channel becomes 64. Kernel size remains same for each and every time, and then the batch normalization we have added and value, and finally the 10H. 10H is particularly used to scale the output pixels to the value of a range between -1 to 1. That thing is matched with the normalization that we have used this particular rate during the normalization of the images that we have given as an input to the model. So to match that thing, we have used particularly 10H at the end. So I would wait for just for a minute so that you can, if someone is lagging behind, they can complete the task till here. Then we will begin with the discriminator model. So there are some questions. I can answer some of the questions for the time being. Uh, Abdul has asked that what is meant by augmenting the data. Augmenting the data means increasing the data that look similar to the original data. So these augmentation techniques actually help the model to train well. So because if we are having less number of images or less data we are having, so we require to increase the number of these images. So for those increment purpose, this augmentation is required. So these similar looking images can be created. That is what GAN is going to do. So GAN, the generator model particularly make fake images so that the similar looking fake images would be generated and those can be supplied to the that can be used for training. Uh, if we do train equals to false, then we cannot use this data for training, right? And what does transform equal? Train equals to false in the second cell, second or third cell means that it was having this data set. So part 10 data set has two types of set of data. One is train, another one is test. So we require train data for this model building. So we have used the train data and we have set it as true. So that particular set would only be getting downloaded for our purpose. And transform equals to transform means transform we have defined over here to apply this transformation on the data that we have downloaded and made the that we have taken over here that we have supplied over here. So transform means normalizing and the conversion to tensor form. That thing we have done here by passing it to the transform. Upsampling is required for upsampling the features by factor of 2 means if it was 8 by 8 over here, so it is going to increase by 60, going to increase to 16 by 16. So it would become next time 16 by 16 dimension, then 32 by 32. So whatever factor we are going to increase, that multiplied by that, it is going to increase. Okay, so we will now begin with the generator discriminator model. So for again, we will make a class that would be having discriminator. So the task of discriminator is to uh, identify real images as real and the fake images that are generated by the generator, classify it as the fake images. So it also gets trained so that it can learn to identify better the fake images. so that it can robustly identify that whether these images are fake or real. So we are building the discriminator this time. So someone has asked why this thing is used here in Python. The init that you have also answered it in your chat. Yes, this init is used as a constructor in Python. So that is why we are here building the constructor, and then we are defining the super and passing the discriminator that would be taking the real images and fake images, and it's going to classify whether it belongs to real category or the fake category. Discriminator, comma, self dot init, and then we have a sequential model again. Previously also we have made a sequential model for the generator. Again, we are about to make the sequential model. nn dot sequential. Uh, Here again we are taking a convolution layer, conv 2D layer, conv 2D layer with the input channel as 3. An RGB image would be given. Output would be of 32. Out would be of 32 channel size. Then kernel size is set as 3 again. Then we have stride of 2. Padding as 1. Then this time we are using leaky ReLU. Most of the things that in this code are used are based on the model, DC GAN model that was proposed by Ian Goodfellow. Uh, Most of the functions that are used are similar to those. Why we are using leaky ReLU in the discriminator was used there also. So we are building a 2 or 3 layer convolutional neural network, GAN network here. So again, a dropout layer is used. Drop out for avoiding for better training, 0 point with the factor of 0.25. Then conv 2D neural network dot conv 2D 32. Here the out channel was 32. I've given the in channel as 32 here. So the out channel in this in this layer is 64. Kernel size is set as 3. Stride is set as 2. And padding as 1. Uh, Model building is up to us how we can use the layers and how we can use the uh, arguments that are given inside it. That is up to us. So neural network dot next time we are giving the zero padding, zero pad to 2D. Here I'll be using 0, 1, 0, 1. So it is going to add the zeros at the right side of the feature, then it is going to add 1 to the bottom of the feature. So first 0 means left, then right, then top, and then bottom. So where we are about to add zeros, where there we have set 1. Then nn dot batch norm batch norm 2D, '64, dot leaky ReLU. Again, we are using leaky ReLU for linear non-linearity, adding of non-linearity. Then I have a dropout of 25.25. Then again a con 2D layer. This con 2D layer, I would be having an input dimension of here I have used 64 out, so I'll be using 64 here. And then the out channel as 128. Kernel size remains same, padding and stride. These things are given. Then again, let's add the batch norm. Batch norm, leaky ReLU and dropout. Once again, I would be adding it. So batch norm would be of 128 dimension, 128. And then we have leaky ReLU of 0.25. Then dropout 0.25, con 2D. Then once again, let's add con 2D, one more layer of convolution. One more layer, let's add one more layer of con 2D, where the input this time is going to be 128 channels. Then the out would be 258, 256. Kernel size remains same. This time, let's give the stride of 1 and padding of 1. So the batch norm would be having 256 as the dimension, leaky ReLU, and then the dropout. Now, finally, we are going to flatten the layer. So we are applying the flatten layer. So neural NN dot flatten. To flatten the dimension stack for here, flatten, then NN dot linear. Linear, where we would then reshape it to the dimension of 256 by 5 by 5 and 1. So we are reshaping the one dimension that is going to occur from the neural from the flattened layer. So we are reshaping it to the size of 256 by 5 by 5 and 1. So 5 by 5 comes from the dimension that would be present from these at the end of this convolution layer. So based on that, I have directly used the 5 by 5 dimensions. And then finally, it would be having the output in form of one type, like it would be either be a real image or a fake image. So to tell that whether it belongs to a real part or a fake image, we'll be giving a activation as sigmoid at the end. So sigmoid is given, which would be giving the probability answer in the terms of probability, so that it tells the highest probability is in terms of the real image or fake image. Depending on that, it is going to answer the thing. After this, again, we'll have to make the forward pass. So def forward, where I'll be giving self and then pass the image and validity. Validity equals to self dot model and pass the image inside it. So it returns the validity that whether it belongs to the real or fake. It is the real image or a fake image. So it tells that. So once uh, we have defined the discriminator, we can now begin with the training of the model. So once let me once tell you some of the things about the discriminator, that the job of this discriminator is that it takes the real or fake images and it outputs a single probability that I was telling over here, that it gives a single probability that actually tells you that whether it belongs to the real as 1 or fake as 0. And then it this custom neural network is defined for this class, like everything is defined inside this custom neural network, the sequential model that we have given. So initially it takes the input and it stacks these layers inside it, and then finally it gives the probability that whether this image is belongs to the real or fake part. So the depth forward self image, this part tells that it takes an image and it passes it through the model and tells the validity that the scalar, that is the scalar value, that 0 belongs to the fake one and the 1. If it returns 1, then it belongs to the real image. So these things would be defined later when we are about to train the model. At that time we will be defining these things. So I wait for a minute, for half a minute, so that if someone is lagging behind they can complete the task, and then we'll begin with the giving the optimization optimizers. We will be setting up the optimizer loss function and then building the model, training the model. Uh, So let me answer one or two questions till that time. Uh, the dimension of out channels in conv 2D should be of our choice. Yeah, it can be of your choice, but in a factor of 2 to the power something. So it was 2 to the power 7 over here. So we have used 2 to the power 8, 256. Then next time we can use 5 and 2. That is 2 to the power 9. In that terms, we can use. The data set that we are using is the online CIPAR 10 data set. We are downloading it from the online part, and then we are using for augmentation purpose. So the someone has asked why we are using dropout. So dropout is basically used to prevent overfitting and it improves the generalization. So that is why we use dropout in between the after the convolution layer, so that overfitting can be avoided and performance can be increased. It is up to you how to use padding. We can use somewhere else. It was my choice for adding padding in that way. It depends on you how you can use. Okay, so after this, we begin with the next part where we'll be giving the loss function and the optimizer. So we are about to define the generator and discriminator and initialize them. So we will be writing generator is equal to generator and then pass the latent dim that was initialized as 100 and to device. Discriminator is equal to the discriminator model that we have made, that we have to give. So discriminator and to device. I will tell you why we are giving here to device. First of all, let's write it and then I'll discuss to device and then define the loss function. So the loss that we are using is binary cross entropy loss, adversarial adversarial loss is equal to uh, nn dot bce loss, that is binary cross entropy loss. Then we have optimizer for generator and separately we'll be defining for the discriminator. So we have optim dot Adam. Then we pass generator, parameters of the generator inside it, generator dot parameters, and then the learning rate. We have set the learning rate as 0.0002. So we'll be directly giving that learning rate here. Then we have betas we have also defined. So the beta 1 and beta 2 we have to give so that the model training would be done according to that, and these would be required by the Adam optimizer that we have chosen for the training purpose. So similarly, we have to make an optimizer for Hello. Sorry, I got disconnected. I hope that I'm audible. Can someone respond that am I audible?
Yes, ma'am. Yes, ma'am. You are absolutely audible.
Okay, thank you. Sorry, my network got down, so I got disconnected. Okay, so I was telling that we were using the optimizer and the loss function. So here I am creating an instance of generator and discriminator. So the purpose of these particular line of code is that we are writing the code so that here in the two lines, if the GPU is available, then these things can be moved on to the GPU, or else if the GPU is not available, it can process the things to the CPU on the CPU hardware. So it is giving the appropriate hardware on which the models can be trained. Then the next line tells the binary cross entropy loss that is used to train both generator and discriminator. So the discriminator must classify the real image as 1 and fake as 0. The generator tries to fool the discriminator to classify fake images as 1, and this is the standard loss function for the binary classification. So finally, we set up the Adam optimizer for both of the networks, and the generator dot parameters and discriminator dot parameter tell the optimizer that which particular weights are to be updated. So these two things that are written inside the argument of optim.adam tell the weights that are to be updated. The learning weight that we are using is 0.0002, and then the beta and beta 1 and beta 2 are the two parameters that control the Adam optimization moving average of the gradients. So these two things are the parameters that control the momentum of the Adam optimizer. So it controls the 0.5 controls the moving average of the gradient, first of all, beta 1, and beta 2 controls the moving average of the squared gradients. So these two things are there. Then the next we will go for the training of the loop. Training the two of the model, the generator model will be training. So let's begin with the training part. For this, we'll be requiring a loop. We'll be requiring a loop with which we'll iterate the data loader and pass the images inside it. And then these images would then begin with the uh, generation of the new or augmented images. And then after that, what would be happening that the discriminator would classify these images as real or fake ones, depending on what it is going to classify it as. So let's begin with the model building. So for epochs, the number of epochs that we have set is currently 100. For more number of epochs, you can train and set the range in number of epochs, range, and pass number of epochs. Then we have for I, comma, batch. On the batches, it's going to iterate in enumerate data loader, and then it convert to the list to tensor. So the real images, first of all, we'll be defining some of the things that the how these real images are, how these fake images are. So real images is equal to batch of 0, because the images, the batch the batch of images consists of two things. One is the images, and another one is the labels that are associated with these images. So we only require currently the images. We do not require labels. So for that, we are writing batch of zero, so that the first dimension that is there, that is the image part, that uh, would be used by our model. Then we have valid is equal to torch dot once real images dot size of zero, and then fake is equal to torch dot zeros. So we are setting a tensor that would be having uh, the real images, a tensor that would be specifying the real images with ones, and the fake images would be set with the values of zeros. So torch dot zeros, where real images would be passed inside it, real images dot size of zero. Here, one more thing we have to give is one comma device. The device that is being associated, that is whether it is CUDA or the GPU, that depends what which thing we are having. If we have CUDA environment, then we can associate that to the model. And to both of the things, we'll be giving the device. Earlier, we have defined this. So this time we have to use that we have defined earlier. And then we will configure the input. So we'll be configuring the input by real images. Real images is equal to real images to device. So simply we are using these things for giving it to the GPU if that is present. So it can be directly gone to the GPU. Otherwise, it gets trained through the CPU. So the first loop that we have written, let's first understand that what this loop is doing. It loops over the training process for a set number of epochs. So we have set it to 100 epochs. So it is going to train for 100 number of epochs and complete the passes through the complete data set. Then we are using an enumerate data loader for batch, for I and batch. So each batch contains a small group of images. We have used a batch of 32 in our initially that we have defined. So it defines a small group of images over here. Then we have batch zero here inside this that I have explained, that it actually uses the image tensor that we have with that actually CIPAR 10 dataset has two things. One is the image and another one is the label. So we only require images. So to use that image, we are using batch indexed with zero that would provide only the images. And then this batch comes from the data loader. And in PyTorch dataset, this typically these tuples, images, these are going to go into the image tensor that we require, and it is going to go inside the GPU that would be allotted. Then we have valid that tells that the real images, these real images belong to the these real images would be associated with ones, and the label for real would be one, whereas for fake it is going to be zero. So real images dot size of zero means batch size. It simply says batch size. For that thing, the coding writes as batch size 32 that we have used. Uske liye, for that thing, we have used real images dot size of zero. Then we have to fill this batch size with one, whereas the another one would be filled with the batch size of zero. So these two things that we have given here, label of 1 would be given, and then the label of 0 would be given. And then we have real images that we have given it to the device, and finally that goes to training. So after this, the important thing that we are about to do is we are about ready to train the discriminator. So now we'll be writing code how the discriminator would be trained. Train discriminator. For this, we have to set the optimizer. So first of all, let's write optimizer underscore g dot zero grad. Zero underscore grade, so that the gradients that are there, those would that were previously there in the during the training, those can be flushed out with the zeros, and from beginning the training can be done. So optimizer would be then for the during the gradient learning of the gradient, these things would be done. Then after this, we have to generate a batch of images. So we'll be generating the batch of images by using gen underscore images, where generator would be given Z, the noise, the latent noise vector that we have supplied, that would be given, so that it can build the it can build what the new generated images for the augmentation purpose. So sorry, I have written discriminator. We are actually writing training the generator right now. First of all, we are writing the code for generator. So then we'll have to define the loss. We have given the loss. We are now during the training, we are setting up the loss function. So we have used the loss as BCE. So adversarial, that variable was named as adversarial loss. G loss equals to adversarial loss. Here we have given this. So similar thing we are using here. This was defined as binary cross entropy loss. Discriminator gen underscore images. So we have supplied the images that are being given with the latent noise vector, so that the generator can now generate new images, new fake images, and the discriminator can identify whether it belongs to real images or fake. So then we have valid, that was set as torch.ones, that was set as ones. Label was given as 1. So generator would be generating with the label of 1. And then the backward pass, g underscore of loss dot backward, and then optimizer g loss dot backward, optimizer underscore of g dot step. So we'll be dealing with these set of lines are for generator, training the generator. Then let's see what these lines mean. So during the train generator, the first thing that we have written is optimizer dot zero dot grade. It actually clears any of the previous gradients that are stored in the generator. So it clears those up and then begins the training. It always do all these types of things before computing the new gradients to prevent mixing so that the mixing between the previous versions and the new version would be avoided. For that purpose, this line is written. Then we have generator Z that is passed in gen images. Here, it takes random noise Z and it generates the fake images. So to generate the fake images, this Z is being passed inside the generator, and these generator actually creates the new images that are completely look like with the real ones. Then the adversarial loss would be given, that would be given as the this generator loss, where the discriminator is going to try to judge whether the generated images that this generator has generated, that these are real or fake. So that is why discriminator generated images is given. And the valid is a tensor. You remember that valid is a tensor that we find in the previous set. Here, here as torch dot ones. So this is a tensor of ones because the gender wants to discriminate and to think that its fake images are real. So to for those types of things, valid is given over here. So it wants the discriminator to think, to fool the generator wants tries to fool the discriminator by making it think that these fake images are actually the real ones. So for that purpose, valid is given. And then we have adversarial, then we have G loss dot backward. So here it computes the gradients for all the weights in the generator based on how badly it failed to fool the discriminator. So the purpose was of the generator was to fool the discriminator. So it computes the gradients for all those weights in the generator in which it has failed to fool the discriminator. Then finally, the optimizer G dot step, it tells and updates the generator's weights using the gradients from the backward steps. So this basically makes the generator better at the at producing the realistic look alike images every time. So this was about the generator. Now let us make the discriminator. Let's once make the discriminator code. So for the training, let me here add the code for discriminator. Train discriminator. So we have seen for the generator. Now let's see how this is done for discriminator. Again, we have to use optimizer. Optimizer G. We have used here optimizer G dot zero grid. Similarly, we'll be using optimizer D dot zero grid over here. So here optimizer underscore D dot zero grid for gradient flow, and then Z is equal to torch dot ran n, where real images, the batches of real images are given. Real images dot size of 0, so that batch would be given, that is 32 in our case. Then the latent dimension would be given. Latent dim is 100, and then set the device equals to device. And then generate a batch of images. fake images equals to generator, and it's going to generate the fake images. The generator with the passing of the Z, it's going to generate the fake images. Then again, we'll have to give the loss for the adversarial training to measure the status ability to classify the real and fake images. So for that, the loss function would be used. So real loss is equal to adversarial loss and pass the discriminator real images and then valid. Similarly, we have to give fake loss and we have to detach the some of the images from the uh, during the training. So adversarial loss, then we have discriminator, and inside this we have to change fake images, fake images dot detach and pass the parameter as fake. This time it is going to work for not for valid but for fake. So we have defined real loss and fake loss, and then we'll be taking the mean of this. So the final loss would be in terms of the discriminator loss as how much it has correctly how it has identified the correctly classified as the uh, real and the fake images. So based on that, the how these two losses were computed, we'll be taking the mean of these things. Real loss plus fake loss. And this divided by 2. And then we have to define the backward pass. Then we have to define backward pass d underscore loss dot backward and optimizer underscore d step. So this is how we have defined the training of the discriminator. So let's once see line by line what these things are doing, these line of codes are doing. First of all, we are using optimizer d dot zero grad. This is again going to reset the all the gradients from the previous training steps for the discriminator, and it's going to begin with the zero grad, and it's going to reset everything because the reason why this step is done is that because PyTorch actually accumulates the gradients by default. So we must clear all of these gradients before each new of the backward pass so that mixing of these gradients would be avoided. For this reason, these gradients are reset. Then the next step is using z equals to dot rand n real images dot size. So here it creates a batch of random noise vectors, latent noise vectors in a random manner, and these batches would then be supplied. So this latent dim is given as the length of noise vector as 100 in our case. So it generates random values from a normal distribution, and between the mean as 0 and standard deviation is 1. So you are creating, for example, 32 random noise vectors of size 100 in this particular case. Then we have fake images equals to generator of Z. So fake images equals to generator of Z defines that the generator takes these random noise vectors and generates the fake images. So it takes these random images that were defined here and it generates the fake images. So this is the core idea behind the GAN, where the generator learns to make fake images from the random noise that look like the real ones actually. So here that this is the portion where we'll about to generate the new images. Then we have the next line where we'll be next three lines where we'll be measuring the discriminator's ability to classify the real and fake images. So the real loss, it tells the discriminator real images where it predicts the realness of the real images, where the valid is complete tensor with the values of ones, and the adversarial loss that we have used, it compares the discriminator's prediction against the correct label. The adversarial loss that it is going to predict against the correct label, that is one, that is associated with the valid value of one, and how it compute those images wrongly. Then we have fake loss. So these fake images would also be there. So first of all, let's see why fake images are detached. So we detach so that these gradients does not flow back to the generator while training the discriminator. So because so that these the gradients that are flown back for these types of for these images does not flow back. So for that thing we have detached it. And discriminator fake images tells us that it predicts the realness of the fake images. Earlier we have computed the realness for the real image, now for the fake image. So these tensors would be full of zeros. Earlier we have defined. So it would be full of zeros. And then it is going to, this adversarial loss is going to compute, measure how wrong the discriminator is in classifying the fake images. How wrongly it is classifying the fake images. For that, this adversarial loss is computed. And it tells that how well the discriminator can detect fake images as fake. Okay, then we have computed D loss as the average. So this averages the two losses, one for the real one and the another one was for fake images. So the goal is to optimize both of them simultaneously to classify the real images as real and fake ones as fake. Then again, we have discriminator loss dot backward so that it computes the gradient of the discriminator's loss with respect to its parameters in the backpropagation. So it tells the PyTorch that how much should each weight in the discriminator change to reduce the loss. And it uses the backpropagation, a process that is going to compute the gradient by going backward in the backward direction to the computation graph. And then finally, we have optimizer D dot step that finally update the weights of the discriminator using the gradients that were computed in this backward pass in the previous step. And the optimizer that we have used is Adam optimizer that applies this particular update rule. And this step where actual learning, this is the step where actual learning happens and the model updates to improve its further performance. So this was how we have defined the train generator and the discriminator. Both things we have defined over here. Then once the training is done, we also require to see that how these computations are actually looking like. So then the next step will be going for is the going to monitor the progress, how the progress is going on. Progress monitoring. So I'll wait for 1 minute if someone is writing, trying to write, so that they can complete this task. Till that time, I'll answer some of the questions. So uh, if we are updating the weights in optimizer.step and then in the next iteration of the loop, it is set to 0 by optimizer.zero grid, then what was the use of the updating it? Isn't it getting lost in each iteration? So it's not going to get lost, but during the initial setting up at that time, if there was the gradient, it's going to learn by that. So it is going to update the weights accordingly. So let's complete the code. Some few of the lines are there so that we begin with the training and we can monitor how this training is happening. So if suppose uh, let's write if I'll first of all write the code and then explain what each of the line is doing. So we are writing here I plus 1 modulo uh, modulo 100 equals to 0. So that what it is going to do is it is going to print the values for the iteration throughout the it's going to print the iteration of each of the steps. So here we'll be printing some of the things that we are writing, the the number of the epoch, then we'll have to print the loss that we are using in the previous, we are computing in the previous steps. So these things would be written. So epoch and then epoch plus 1. Epoch plus 1 and slash number of epoch. Uh, these things, let me, since I'm going to explain, I would directly begin with the training so that your time is saved, and I will explain this line of code directly to you so that our time gets saved, the time being. So here, till this time, let me write that we are here, number of epochs. Then we have to write the batch, that is batch of Okay. So sorry, I got disconnected. So what I do is I'll directly copy the code and I will explain this. So I was about to write this. Till here we have written everything. Till here we have written each and everything. From here we are beginning with the progress monitor. This particular code only tells us that the how the progress is going on during the training time. So each here this loop tells that every 100 batches, this it prints the summary for each of the 100 batches of the current training progress. So which epoch we are currently in, which batch of that epoch we are progressing in, these type of things are given inside it. Then another thing that we want to print is the discriminator loss and the generator loss that we have computed in the previous step. So the discriminator loss, D loss, and the generator loss is also given here. This particular loop helps during the this helps us to monitor the training process and it detects the problem. Like sometimes the discriminator overpowers the generator. So it has very low discriminator loss. So it is also not a good sign, or it has high generator loss. So these types of things tells us that the discriminator is actually overpowering the generator. So, or else there can be one condition that the generator produces bad images. So these loss is not decreasing. Then we have another set here where we are saving the generated images. This particular loop I have made for saving the generated images for each of the epoch, where we'll be displaying these images, generated images for each of the 10 epochs. Let's see how it does. Uh, Once we have set the generator and discriminator model, I have already done the training at the background. I have already done the training previously. So what this code does is the previous code prints the epoch 1 of 100, and then it tells the which batch is going on from complete batches. Then it tells the discriminator loss and the generator loss. This was what this particular this loop was doing. Then next loop was iterated for printing some of the number of generated images. See, to visualize that whether the images that are being generated are good or not. So let us see that after completion of the 10 epochs, for each of the 10 epochs, these are the generated images. Since I have only trained it for 100 number of epochs, it has not learned nicely. So it is not displaying a good result, but in fact, we can like in this blur manner also, we can see that there are some of the automobiles or the somewhere we see images of frog by visualizing it. We can understand that yes, there is a truck or there is a any horse or some type of animal it was trying to build. So by after every 10 epochs, we have seen the visualized the results, how these generated images from the generator looks like, and how much is the result in quantitative manner each time it is printing. So these were the two loops that we have used in the previous code, in the previous cell that we have used. So for 10 times these results were visualized and generated images were seen. Okay, so this was about the GAN that we have built. You can train it. I'll be uploading this file, and you can train this model for more number of epoch and see that there is going to be a drastic effect for this generation. of the new images. Then let's discuss one more DC GAN that was developed by Ian Goodfellow. So he has used fractionally strided convolution or the convolution to the transpose for upsampling the features and convolution layer and batch normalization. That was his idea for building the generator model. And then I have used a data set named as yoga pose data set. For that data set, it was having initially 300 around, 700 around images. And that data set, I have tried to augment it. So it was having different types of yoga pose. So initially, I have used some of the libraries, and then we have used some of the libraries and some of the parameters that were used, some of the variables that were used by the model DC GAN that was proposed by Ian Goodfellow. So initially, the idea was using the setting up the data set root path. So this is my path of my library. This particular path is there in my library where yoga pose detection data set is present. And then we are using some of these variables where number of workers tells that how many, if we are having a number of GPUs, so these can be worked in the parallel manner. So in two different parallelly we can work on. Then batch size, image size is initially given. Then the number of channels in the training images is set up as 64 initially. Then we have the number of channels in the training images. Since it is a RGB, red, green, blue channel images, it has 3 channels. Then we have latent vector size as 100. Then we have feature maps of generator. All these variables were initially used by the DC GAN. So that is the reason that we are using over here. But I have already trained this model for 3000 number of epochs. Then this paper has used 0.0002 learning rate. So we have also explicitly used this thing directly. Again, the normalization is done for the images. Same normalization is there. Then we have also used resize and center crop, these augmentation techniques over here, and then loaded data. Then we have made the data loader for this data set, and then given the batch size inside it. Again, if we have the CUDA environment or GPU, then the generator and discriminator models can be run on this CUDA environment. So we can check the condition that whether this GPU is more than 0 or not. Otherwise, it is going to work on the CPU. Then we have to, then I have simply written a simple code for the visualizing the images that are present inside this data set. So this data set basically consists of 6 classes of images, but here some type of downside warrior pose, some of the famous poses are present inside this data set. So here we have displayed some number of images in this grid pattern. Then we have finally, then after this, we are about to set the custom weights for initialization purpose. So initially, the weights are not randomly given, but we have initialized it in terms of initializing the generator and the discriminator model by giving the mean and standard deviation for setting up the weights. So here, if this was also given in the paper itself. So they have used the mean and the standard deviation for the convolution layer for setting up the weights. Whereas for the batch normalization, they have used mean as 1 and standard deviation as 0.2. So the generator model of the DC GAN, deep convolution GAN, looks like something like this, where they have 4 convolutional layers followed by the batch normalization layer and the stride of 2 and padding also involved it. So based on this, they have made the generator code similarly, but the difference that from the earlier model and the model that earlier model that we have built and the model proposed here, was in terms of the convolution transpose 2D, that there I have used upsampling for upsampling by the factor of 2, but the authors in this paper have used convolution transpose 2D. So initially they have used convolution transpose 2D, and given the NZ value that was given over here initially, that NZ was 100, that is the latent vector size, the noise vector size, with 100. Then NGF, whatever the NGF value, the initial feature size of the image that was given, I think it was 64. So NGF was, yes, 64. So double of that we have used. So the authors have used 8 times of NGF is used over here. Then the kernel size is set as 4, and stride as 1, and padding is 0. Then a batch normalization layer, then ReLU activation, then again a con transpose 2D. So this was their architecture. So this was the architecture that DC GAN was given. Then the generator was set up to the device if GPU was present. So on device it was set up, and in parallel, if there were multiple GPUs in parallel manner, it can perform. And then then we have printed the model, sequential model that was developed in the previous here in this code. And then remember that we have also used the activation 10H in the generator model. Why? Because we have normalized the images in the range of -1 to 1. So here also, when these images are finally the last features that would be given, that would come in the -1 to 1 range. So for that, we have given the last activation as 10H. Then we have a discriminator model in the similar manner, where convolution 2D was used, leaky ReLU, batch normalization, and finally a sigmoid activation was used for classifying the images that were generated by the generator. The discriminator is going to identify it as real or fake. So this sigmoid activation would give the probability in terms of 0 and 1, that whether it is real or fake images, how correctly it is going to identify. So we'll be creating the discriminator, and again the GPU would be given to this. So here is the code for allotting the GPU or multiple GPUs if these are present. Then the activation loss, then the sorry, the loss function that is used is the binary cross entropy loss that we are using here. And then starting up the setting up the optimizer Adam, where the parameters would be used with the netd dot parameters here, inside which where these parameters would be set for during the training of the generator, where as well as the discriminator. So here beta 1 was given 0.5 in the original in the paper, it's and 0.999 for setting up the optimization during this training of the Adam using the Adam optimizer. These both are going to control the how it is going to train the model. So for controlling the momentum, these two optimizers are used. Then we have a training, again, the training of the loop that is similar to what we have done before. Similarly, forward and backward passes would be given, the gradient would be made 0 initially, and then and if the fake images are there, we have to detach the GPU so that these learned weights are not flown back to the in the backward pass. And then finally, the mean of both the fake images and real images would be taken using outplot. We have done the previous one. We have done the fake images and real images divided by 2. So it is going to compute this, and then the gradient would be forward backward would be computed. And let's look at the output that is being generated over here, where this loss is there, and the sorry, discriminator loss and the generator loss. So the discriminator loss is less, whereas the loss of generator is high, where it is actually the discriminator is getting confused, is actually getting confused by identifying the fake images as the real ones. Uh, so these both generator and loss and the discriminator's loss is given, whereas the probability that how much discriminator is correctly identifying this probability is given using d of x, and next is the d of g of z that was explained in the theory class, that is also present inside this code. Then finally the loss is being plotted. This is a simple code for uh, uh, plotting the loss throughout the iteration. And finally, an animation is there for printing how these fake images would look like. So somewhat the here it shows that it has somewhat tried to generate the images, but since the discriminator was getting confused a bit during my training that I have observed, generator was generating the fake images, but discriminator was not correctly identifying that these generated images does not belong to real ones, these are the images. So it was getting confused. That's why it is not running well, and it's not getting generated very well images. But by increasing or changing some of the change somewhat inside the oh, sorry, I got disconnected. So this was all about the simple GAN as well as the DC GAN, the model that was posed by Ian Goodfellow. So this is final result that after doing DC GAN, I would be sharing both the files so that you can train it on your data set of your how images are generating image. One of the questions there, did we do detach? Could you please, dot detach was used for detaching the fake Thank you, participants, and sorry from my side the net uh, for the problem that occurred due to net. Uh,
Hello, ma'am. Can you hear me?
yeah, Gaurav.
Okay.
Uh,
Ma'am, shall we conclude the session?
yeah, you can conclude. This was all from my side.
Okay,
DC GAN
ma'am.
and the GAN that we have customized GAN that we have discussed, it was completed from my side.
Yes, yes, ma'am. We are very grateful for the knowledge, ma'am, you have imparted today, and it's an honor to learn from you. And thank you so much, ma'am. And one request, ma'am, that please share the resources. You have already told you will share. So thank you
Okay,
so much for
sure.
that. Thank you
Thank
so
you.
much, ma'am.